We're going to do another related rates problem, mainly because you can never do too many related rates problems. Okay, so we're given all this information about rates of change. As we read this problem, we see we've got something sliding away, something's changing. We're given a rate here, there's a rate of change, and we're asked to find these other rates of change. So that's what tells us we have a related rates problem. This actually is two separate related rates problems because it asks two different things, and so it kind of has the same initial setup, but really two separate problems. So we're going to do part A first here. Okay, so read the problem, draw a picture. Okay, so I've got a ladder leaning against a straight wall on level ground. My ground didn't look very level there when I first drew it, did it? There. Okay, so ladder leaning against a straight wall on level ground. So here's our wall, here's our ground, there's our ladder. So we might notice there's probably a right angle there. The base of the ladder starts sliding away from the wall. All right, so the base of the ladder is going away from the wall while the top of the ladder slides down the wall. Okay, when the base of the ladder is 3 feet away from the base of the wall and sliding at a rate, we're asked to find something about the rate of the top of the ladder. Okay, so I need to label some variables here. We've got the base of the ladder, really this distance here from the base of the ladder to the wall. Just because of the way I have this kind of set up, it sort of looks like X and Y axes. I'm just going to label that X, but you could maybe use B for base or whatever. And then I'm also asked about some information about the top of the ladder to the ground. And again, just because of the way I have my axes set up, I'm going to label that Y. And so we've got a couple variables here that we are asked about and given some information about. So we're going to make our little chart, variables and rates. Okay, there's another piece of information in this problem though, and we haven't really had this in too many problems yet, but in a couple of them, where we have a fixed quantity. That ladder, that 15-foot ladder, that is going to stay fixed. So that distance right there is staying fixed. The distance along what's really the hypotenuse of this right triangle here is fixed. So that's not really a variable. Okay, but I do have a couple variables here. I chose to label them X and Y. So whatever other letters you might have used here, X and Y, and then I have rates for each of those, dx dt and dy dt. Okay, so when I read the problem here and kind of fill in that information, the base is sliding away, the top is sliding down. When the base is 3 feet away, so that's my X, from the base of the wall and sliding at a rate of 0.5 feet per second. So I want to think a little bit about whether this rate of change would be positive or negative. So my little arrow on my diagram might help you think about that. Since that ladder is sliding away from the wall, that X distance is going to be getting bigger. So this is a positive rate of change, 0.5 feet per second. And then it asks us at what rate is the distance from the top of the ladder to the ground changing, so that's what I need to find. Okay, so there is the information that was given in the problem. I now need to think of an equation that relates those variables. So we've got a right triangle here, so part of the key to doing this problem is recognizing you have a right triangle. You're asked about some things about the sides of the right triangle. You're given a hypotenuse of the right triangle, and so you should probably pretty quickly get to thinking about Pythagorean theorem, a squared plus b squared equals c squared. Or if I use the variables and quantities in this problem, I would have x squared plus y squared equals 15 squared. And since that 15 squared is constant, not a variable, I might go ahead and just square that out. So x squared plus y squared equals 225. Okay, so there's my equation that relates the variables in this problem, and then I want to differentiate implicitly with respect to t on both sides of that equation. So I'll just squeeze in a d dt right there. All right, so on the left side of the equation, I will have 2x times dx dt plus 2y times dy dt. And then on the right side of the equation, the derivative of a constant is just going to be 0. So just 0 on the right side. Okay, and then at that point, we want to look at the information we're given and plug in the numbers we have and solve for the one we're trying to find. All right, so I'm just going to do some labels here. The dy dt is what I'm supposed to find. Dx dt, I'm going to plug in positive 0.5 for that. I'm given a value to plug in for x. I need a value to plug in for y, so I'm going to have to do a little bit of extra work here. So I'm going to go back over here to my chart. I need to find y when x equals 3. Okay, so I'm going to use my Pythagorean theorem that I had right before I took that derivative. I had x squared plus y squared equals 15 squared. So I'm going to have 3 squared plus y squared equals 15 squared. I'll get y squared equals 216. 225 minus 9, so y is square root of 216. All right, so there was my work, and that's what I'm going to plug in for y, square root of 216. 216 does contain a perfect square. 36 goes in there, so if you want to simplify that radical, that's okay. All right, but now I'm ready to finish my problem. I'm going to go over here to the side and do that. So I'll have 2 times 3 times 0.5, or maybe I'll write that as 1/2, plus 2 times y, my y was square root of 216, times dy dt equals 0, and now I need to just solve for dy dt. So let's see, I might notice that these 2's cancel, and then if I subtract 3 and divide through by 2 times square root of 216, I should be able to get my answer. All right, so I'll have dy dt equals negative 3 over 2 times square root of 216. As I said, 216 does contain a perfect square, so if you want to rewrite that as 6 square root of 6, you can do a little simplifying here. It's okay to leave it like this, except you should probably label your answers. Y is measured in feet, distance measured in feet. T, the time here, is measured in seconds. So this is negative 3 over 2 times square root of 216 feet per second. Negative tells us that that y is decreasing. We should have expected that if we just thought about the problem. If I want a decimal approximation for this, I can go ahead and get that. I think we get about negative 0.1021 feet per second, approximately. That was part A. There's a part B here as well. It's asking us about an angle between the base of the ladder and the ground. So for part B, I have really another variable here that I'm asked to find. So, all right, actually I think I'm going to erase what I did for part A, and we'll just use the same diagram and chart so that we can answer part B. Okay, so I've erased all of the work we had before. I did keep the answers that we got from the first part of the problem in case we need those for the second part of the problem. But for part B here, it's asking us about an angle. So I'm just going to add to my chart here. I've got another variable that's an angle, and it's asked us something about d theta dt. So we'll actually be finding the rate at which the angle is changing for part B. Okay, so because I'm interested in something about an angle here, I need a relationship between the variables that uses theta. So when you see a right triangle with an angle labeled theta, you should think about sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And actually, any of those methods will work for this problem, but one thing that we might notice about this problem is that the hypotenuse is fixed. The opposite and adjacent sides of this triangle are variables. So if I use a tangent relationship, tangent theta is opposite over adjacent, I'll have more variables. If I use one of the ones that's about the hypotenuse, then I'll be able to use that as a constant. All right, and the other thing I might notice here is that I've got some numbers in my chart here for variables and rates of change, and gosh, those numbers for x sure are a lot nicer and prettier than those numbers for y. So I might choose to use something, my trig relationship, that will relate x and 15, so that's the adjacent side, and 15. I really could do this problem using any of those, sine, cosine, or tangent, but this is actually going to be easier if I use cosine, just because the numbers are a little bit cleaner. Okay, so my equation that's going to relate the variables here, I'm going to have cosine theta is adjacent over hypotenuse, x over 15. The hypotenuse is constant. Okay, and then I want to differentiate with respect to time, so d dt of both sides. Okay, so on the left side of the equation, the derivative of cosine is negative sine, and then I have d theta dt equals, and on the right side, you probably don't want to use quotient rule there. You probably want to think about that x over 15 as 1/15th x, so that it's easier to differentiate. So the derivative of 1/15th x would just be 1/15th, and then times dx dt. Okay, so at this point, we usually plug in our numbers and think about what we're going to do here to solve for what we're asked to find. So the d theta dt is what we're supposed to find. Our dx dt is positive 1/2. All right, and then I need some stuff here to plug in for, well, either theta, or actually maybe easier on this problem to just plug in for sine theta. So remember that sine theta is opposite over hypotenuse. So if I look at my right triangle here and think about opposite over hypotenuse, the opposite side is really y, and the hypotenuse is 15, and I know a value of y at the time I'm interested in, so I'm going to put in the y equals square root of 216. You could also get a pretty messy and ugly answer by trying to solve for theta, but it's handy to notice that I actually can just use the sine as the opposite over hypotenuse because I have that information from part A of the problem. Okay, so plugging in all my numbers here, I'm going to have negative sine theta. So sine is opposite. My y at that instant is square root of 216 over hypotenuse. That's fixed. D theta dt is what I'm trying to find, equals 1/15th times 1/2 on the right side. Okay, so if I just multiply by the reciprocal of negative square root of 216 all over 15, I should be able to get my theta, my d theta dt. All right, so on the right side here, I have 1/30th, and then I'm going to multiply that by the reciprocal of that fraction I had on the left side. I do get some nice cancellation here. Maybe you notice 15 goes into 32 times, and if I want to, I can also simplify that square root of 216. All right, so I can rewrite this as negative 1 over 2 times square root of 216, or if you simplify that even more, you get negative 1 over 12 square root of 6. 216 is 36 times 6. Okay, and then I need to think about my units on this. So paying attention to units on my d theta dt. So one important thing is that any time you are doing calculus with trig values, you need to be thinking about that in terms of radians. Why? Otherwise, the derivatives are not what you think they are. And then time in this problem is measured in seconds. So our rate of change here would be in radians per second. And if I want a decimal approximation for that, I can get out my calculator, and I should get about negative 0.034. Okay, we're going to look at one more example in that next video.